So now we have Iryna Butsky from University of Washington, and she'll tell us about the impact of cosmic rays on thermal instability in the CGM. So take it away.
Yeah, so without further ado, I'm going to talk to you about a project I recently worked on as a pre-doctoral fellow at the CCA with Drummond Fielding and Chris Hayward. And so, broadly speaking, I'm interested in understanding the structure of the circumgalactic medium, which is this diffuse gas that extends out to and beyond the virial radius. And it's shaped by interactions from chemically enriched outflows from the galactic disk and pristine inflows from the intergalactic medium. And the shape of the CGM really holds the imprint of these interactions that govern galaxy evolution. And in particular, I'm interested in understanding the cool phase of the CGM, which contains a substantial fraction of the total galactic baryons, and is believed to accrete onto the galactic disk to fuel star formation. So then it's particularly interesting why some quiescent galaxies also have these massive reservoirs of cool gas in their CGM. And so the question I want to understand is, what's happening to this cool gas? It could be that it is accreting onto the disk and these galaxies are about to start star formation. We just happen to observe them at this awkward phase in their evolution. It could be that the cool gas is accreting, but for some reason it's not cooling to the right temperatures in the ISM. Or it could be that there's something preventing this cool gas from accreting onto the galaxy in the first place, which is a concept that I'll be revisiting in this talk. And one strange thing about cool gas, especially around low redshift L-star galaxies, is that it appears to be out of thermal pressure equilibrium with a hot medium. So here is a plot from Jess Work's 2014 paper that shows the predicted hot gas and cold gas density as a function of radius for a Milky Way type galaxy. So these are theoretical predictions from Mahler and Bullock. And when they measured the densities of this cold gas, it appears that the observed cold gas density is actually a lot closer to what we would expect for the hot gas density than what we would expect for the cold gas density. And if we were only thinking about thermal pressure, this means that the gas is out of thermal pressure equilibrium. Now, if it's out of thermal pressure equilibrium, that means it's very short-lived. And then we'd need some mechanisms to explain how we observe, 40% of all of the galactic baryons just constantly being regenerated. And although there are certainly processes that can generate this short-lived gas, it's unclear if they can account for all of this cold gas phase. And so I'm going to argue in this talk that it's not that the cold gas is necessarily out of thermal pressure equilibrium, but it's not that the gas is out of total pressure equilibrium, it's just out of thermal pressure equilibrium. And this additional pressure can be made up by cosmic rays. So like Christoph introduced in the first talk, cosmic rays can play a very important role in galaxy dynamics. So here's a movie made by Cameron Hummels from the Fire collaboration, showing two galaxies, Milky Way type galaxies, one without cosmic rays and one with cosmic rays. And we see that simulations with cosmic rays have very different ionization structures in the circumgalactic medium. And although there are few direct observational constraints of the cosmic ray pressure in the CGM, we do know that cosmic rays play an important role in the energy budget of the ISM, and so they're likely also important in the CGM. And so if cosmic rays are in the CGM, and when cosmic rays are present in the CGM, they affect the structure of cool gas, I'm interested in understanding how cosmic rays affect the formation of cool gas through thermal instability. And so I'm going to first introduce the concept of thermal instability without cosmic rays, and then build on that for the remainder of this talk. So if you consider a patch of CGM gas that's in hydrostatic equilibrium with a gravitational potential pointing to the bottom of the page, and you assume the gas has no cooling, if you get a small perturbation, so that now there are patches of gas that are colder and denser and hotter and less dense relative to their background medium, in the absence of cooling, the gravitational buoyancy forces will make the cold, dense clouds sink, where they'll experience compressive heating, which will heat the gas until the perturbation is washed out. And in the opposite case, if you have very strong cooling, what happens is these initial perturbations, the overdense perturbations, experience a stronger cooling. So as they sink, the cooling overcomes the compressive heating. So these cold clouds become denser and more cool, which then results in an even faster, more efficient cooling scheme. So you experience this runaway cooling and you develop a multi-phase medium. Now, we can model this in simulations very well, and these simulations have been done by Mike McCourt and Soqing Ji with magnetic fields to show the evolution of classical thermal instability. So here are simulations very similar to this toy model that I just showed. It's a patch of CGM gas in hydrostatic equilibrium with a gravitational potential field pointing down. The simulations are actually twice as long, but since they're symmetric around the midplane, I'm only showing you the top half. And they're initialized with a small isobaric perturbation. Now, simulations on the left have efficient cooling, and simulations on the right have very slow cooling. And that cooling time, or that cooling efficiency, is expressed by the ratio of the cooling time to the free fall time. So simulations on the left are evolved, well, all the simulations are evolved for 10 cooling cycles. So the simulations on the left are actually evolved for shorter physical time than simulations on the right. And so what you'll see is that when you have efficient cooling, cold gas just visibly condenses out of the background medium and starts to precipitate onto the galaxy. And without efficient cooling, there is gas motion, but the cold gas never really condenses. And I'll add that these simulations are scale free, but if you want to apply them to like a Milky Way type galaxy, the size of this box would be about 40 by 80 kiloparsecs. And so moving forward, I'm going to zoom in on parameter space to keep it manageable and only talk about simulations, or at least show videos of simulations where the T cool over T free fall is 0.3. And so I want to understand how the presence of cosmic rays affects this process of thermal instability. And I'm going to approach that in 2 steps. So first, I'll talk about the impact of cosmic ray pressure, which is the limit where cosmic ray transport is unimportant. So these are simulations with just adiabatic cosmic rays where they are just move with the gas. And so I'll focus on just the impact of that cosmic ray pressure, and then I'll talk about how cosmic ray transport complicates the picture a little bit. So now I have a very similar set of movies, only now the different panels show different cosmic ray pressures, which are initialized to be a constant fraction of the gas pressure everywhere. The color bar now shows the slice of the density as opposed to the density projection. And what you can pick out visibly is that with increasing cosmic ray pressure, the cold gas that forms is larger, or forms larger structures, and it's less dense overall, and there's less density with there's less of a density contrast with the background medium. And we can quantify this for a variety of different initial values of T cool over T free fall, for a variety of different initial cosmic ray pressures, to show that with increased cosmic ray pressure, it really does just monotonically wash out the density perturbation, or the density fluctuation. So this is because in the traditional or the classical thermal instability, gas cools isobarically. So this is a 2D histogram of the temperature and number density of the gas averaged over between 4 and 6 cooling times. And you'll see that this hot gas follows lines of constant pressure up until it reaches the temperature floor. And here you'll see a resolution-based dip, like Drummond mentioned, where we're not quite resolving the smallest structure. And I'll also point out that our temperature floor is set to be 5 times 10 to the 4 Kelvin, but in a realistic system, we would expect this temperature buildup to be closer to 10 to the 4 degrees Kelvin. Now, when you add cosmic rays, the pressure support from cosmic rays helps this gas cool isochorically. So especially for cooler gas, which has a larger amount of cosmic ray pressure because cosmic ray pressure is concentrated as this gas kind of condenses, you see a more strongly isochoric relationship as opposed to this warm gas, which approaches being isobaric. And you can see that the temperature of the gas, or the distribution of temperatures, is actually quite similar. And it stands out in this movie, which shows the same panels as the density movie, only now it's colored by the temperature slices. And so the shape as seen by the temperature of these cold gas clouds is the same as it was with the density, but the temperature stays constant between runs. And this is because the temperature is set by the cooling curve, which is an approximation of atomic physics, and it's insensitive to the cosmic ray pressure. And so we can quantify this a little bit more by looking at the cold mass fraction measured at the simulation midplane, or I should clarify, measured at the scale height, so kind of right in the middle of the simulation boxes, as a function of the initial T cool over T free fall of the simulation. And so for weak cosmic ray pressures, the amount of cold gas that forms doesn't really change. But for substantial cosmic ray pressures, and for simulations that are run for a longer amount of physical time, the amount of cold gas at the scale height actually increases. And this is in part due to the fact that cosmic ray pressure decreases the inflow of cold gas. All right, so as a mini summary, with added cosmic ray pressure, cosmic rays, or the classic thermal instability, instead of forming very dense, small gas clouds that precipitate, forms less dense cold clouds that are larger and are less likely to precipitate. But all of this is a strong function of the cosmic ray pressure, which kind of is counteracted by cosmic ray transport. And so, as a very brief overview, cosmic ray transport is typically approximated by either streaming, diffusion, or a combination of the two. And both are approximations to the microphysics of how cosmic rays interact with the magnetic fields. And in the hydrodynamics approximation, you can think of it as cosmic rays moving down their energy gradient along magnetic field lines. And kind of the important thing is that by moving down their energy gradient, what the cosmic ray transport is going to remove cosmic ray pressure from regions where it's most concentrated, so in these cold gas clouds, and then redistribute it to the background medium, which is going to alleviate some of the impacts that cosmic ray pressure does to thermal instability. So this is a movie showing simulations with T cool over T free fall of 0.3, a cosmic ray, or an initial cosmic ray pressure ratio of 1, and the color shows the slice of cosmic ray pressure. And then the different panels show different cosmic ray transport approximations. So the movie on the left was present in the most recent temperature and density movies, and the panels on the right show runs with different diffusion and streaming approximation. And so you can visibly see how cosmic ray transport redistributes cosmic ray pressure into the background medium. And in situations where the cosmic ray transport is very efficient, you actually see a relatively uniform distribution of cosmic ray pressure. And so this has a direct influence on the density distributions of cold gas, or of just the cold and the warm gas. So here are probability density profiles of the cold gas in the simulations, measured at the scale height and averaged over the time periods between 4 and 6T cool. And so without cosmic rays, you have a very bimodal medium. So the densities of the two phases are set by the temperature contrast and pressure equilibrium. If you add cosmic rays, but without any cosmic ray transport, this turns into a very, or the bimodality shrinks. So the density of the cold phase is much more similar to the density of the hot phase because it's supported by cosmic ray pressure. And then as you vary the different possible cosmic ray diffusion or streaming prescriptions, you can have a wide array of intermediate density profiles. And these are inversely related to the cosmic ray pressure ratio profiles measured in the cold gas. So the more bimodal the pressure ratio distribution is, that is, cold gas has a much higher amount of cosmic ray pressure than hot gas, then the densities of the two phases are very similar. And for cases with efficient streaming or diffusion, where the pressure or the cosmic ray pressure is almost the same in the cold and the hot gas, then you get a more bimodal density distribution.
Hey, Iryna, just about 4 minutes. Sorry.
Awesome. Thanks. No problem. All right. But as we've kind of noticed before, how the temperature doesn't change, the temperature distribution stays remarkably similar. And that's again because the temperature of the cold gas is set by atomic physics. And so the cosmic rays aren't changing like the nature of this cold gas, they're just changing the density. And now one thing that's not immediately obvious from looking at these two temperature and density distributions separately is that with cosmic ray transport, the phase or the temperature and density phase actually, or simulations with cosmic ray transport actually fill a larger portion of the temperature density phase, which is unlike simulations with just cosmic ray transport and which is unlike simulations without cosmic rays and simulations without cosmic ray transport, which may explain some of the photoionized oxygen 6 that's observed in the CGM. Now, so mini summary for this last section is that overall, cosmic ray transport kind of bridges the gap between classical thermal instability and thermal instability with cosmic rays, but it also adds nuance and fills a larger phase space. So kind of indicated here by the shading of the temperature colors. Now, as I approach the end of my talk, I kind of wanted to present the family portrait of all the simulations that I ran for this project. And so this is a plot looking at the average density contrast. So the average density of the cold phase divided by the average density of the hot phase as a function of the cosmic ray pressure ratio to the gas pressure in the cold cloud. And every point is it's an individual simulation. The colors of the points show the cosmic ray transport. So green circles are cosmic ray runs with advection only, and then red have diffusion and blue have streaming. And the overplotted dashed lines show our analytic predictions for this density contrast as a function of cosmic ray and magnetic pressures. And so this dashed line is the prediction for cosmic rays that only advect. So that, which depends on how cosmic ray pressure scales with gas density, which is in the advection case is 4/3. But once you introduce cosmic ray transport, that scaling doesn't hold. And there's a lot of uncertainty about what that scaling would be. So here we plot two kind of potential scaling relations, but I'm going to highlight that this is something that needs constraining in the future. And importantly, we make predictions for the size of these cold gas clouds. So kind of the accepted characteristic scale of cold gas clouds is set by the minimum of the sound speed times the cooling time. And we make, and cosmic rays affect both the sound speed and the cooling time. So we make a prediction for the relative size of this cloud with cosmic ray and magnetic pressure as a function of the thermal only prediction for the cold cloud size. And there's a more kind of detailed derivation and expression in the paper, but in a cosmic ray dominated medium, so these are simulations that are all the way on the right side of this plot, we expect the size of the size ratio of the cold cloud to be a function of the temperature contrast between the cold and hot phase. This gamma effective is the scaling of the cosmic ray pressure and gas density, and the cosmic ray pressure over the gas pressure. And so for cosmic ray dominated medium, the size of the cold gas clouds can be up to 100 or 200 times what we would predict without cosmic ray pressure at all. And so in summary, I think accurate interpretations of the EGM observations need to account for the presence of cosmic rays. And in this work, we've kind of highlighted how cosmic rays can help explain observations of low gas densities and observations of galaxies that are quenched but have large reservoirs of cool gas. But moving forward, there's still a lot of work to do with constraining models for cosmic ray transport, because they will have very important quantitative effects to this. So thank you for your time. I'll gladly take any questions you have.
Great, thanks. And it's a super interesting project, so thanks for sharing it. Yeah, we do have 8 or 9 minutes for questions. I have plenty of questions. I could fill that entire time slot if we want. I guess I'll actually wield my power as moderator to ask a quick question. So in the streaming case, you have wave damping and subsequent heating of the thermal gas when you have a cosmic ray pressure gradient, or a pressure gradient that's field aligned. So here you have this case where you have a magnetized medium that's compressing, so you must be compressing the magnetic field. You're also compressing the cosmic rays. And so where's the pressure gradient, and then where's the heating happening? Is it happening at the cloud kind of interface between the cold gas and the hot gas, or is it happening mainly in the cold cloud region?
That's an excellent question. So we did include simulations with and without kind of an explicit cosmic ray heating. So because, so the simulation is very idealized. So the cooling follows a simple power law, and then heating to maintain global stability, we just balance the total cooling at every vertical layer. And so in that context, you can convince yourself either that, this contribution from cosmic ray heating in the streaming case should be part of the kind of global balance, or it can be a perturbative source. And so when comparing simulations with and without that explicit cosmic ray heating term, we do see some difference. Actually, this is kind of the difference on the measured quantities. So these are simulations with and without cosmic ray heating, with a cosmic ray pressure equal to the gas pressure. And for the most part, like the quantitative difference is relatively slight, and kind of visually, it seems to, it's hard to tell if the majority of the heating happens at the cloud boundary, because the cloud boundaries are visibly smaller, but there's also a decrease in the cold gas just in the core. I think this would be something like that. I think it'd be very interesting to look into this in like a dedicated study of a more like resolved individual like 3D cloud. But in these simulations, like the cosmic ray heating didn't affect the global properties very much.
Okay, yeah, great, thanks. So let's hear from Pratik.
Yeah, thanks for the excellent talk, Iryna. So I had a question. So you motivate your setup observationally showing this work at all 2014 result that, the cool gas diagnostics show that the density of the cool gas is actually much lower than what you expect in pressure equilibrium. So the question is, can we sort of test? So that's like a coarse-grained picture in some sense. Can we like look at individual observations like the galactic center filaments and the like filaments observed in galaxy clusters and put some constraints on the cosmic ray pressure versus magnetic pressure?
I think right now that's something difficult to do, in part because all these observations are so tied to like the galaxy evolution. So like, it takes time for the cosmic ray pressure to build up in the halo. And so in order to accurately address that, you need to kind of model and have self-consistent cosmic ray feedback to see like how long it would take to build up that cosmic ray pressure in the halo. And you also need constraints on the cosmic ray transport, because especially if you look at, a plot like this, depending on what your approximation is for cosmic ray transport, very different kind of amounts of cosmic ray pressure can give the same density contrast.
Right. So, I actually wanted to know about like observations, like
I see.
like filaments in galaxy clusters. People have put constraints on magnetic field strengths, right? And for example, Christoph's first talk, he showed these galactic center filaments. So you can put some constraints on magnetic fields. Can you also put from, say, synchrotron emission, some sort of equipartition arguments? Can you put constraints on cosmic ray pressure? Because magnetic fields will also give almost a similar effect as far as isobaric versus isochoric goes, right? In terms of cooling, right?
Yeah, that's a great question. I'm not sure how to place direct constraints on the cosmic ray pressure as opposed to the magnetic field pressure, but that is definitely something I'll be thinking about in the future.
Okay. Yeah, thanks.
Cool. Let's go to Christoph and then we'll go to Ryan.
Yeah, I wanted to answer Pratik's question. So that's quite easy because the cosmic rays run into the ambient gas protons, and this will actually create ions which decay into secondary electrons and gamma ray emission. And so the non-observation of gamma rays gives an upper limit on the cosmic ray pressure, and the observation on the radio emission, of course, knowing the magnetic field, which is something quite tricky to get, but this allows you to get also an upper limit on the secondary electrons and therefore an upper limit on the cosmic ray protons, because there could be primary electrons that typically dominate over the secondary electrons.
So what is sort of the, is it magnetic field dominated or cosmic ray pressure dominated? So if you plug in the numbers. Right.
So we did this experiment, in fact, in galaxy clusters. So it's more tricky in a galaxy because this is full of gamma rays and radio emission, but because of the star formation, so it's difficult to sort of basically look at the CGM. But if you
I think we can talk about it
let's move this to the discussion later on.
Yes,
exactly. Yes.
I think yeah. Okay. Thanks.
Yeah, Ryan, go for it.
Thanks, Iryna. That was a really interesting talk. So I was wondering if you could, is somewhat related to Pratik's question, I guess, if you could talk a little bit about the magnetic fields in your simulations. I think I noticed one slide where you mentioned plasma beta of 10 and 100, and I was wondering if you, although that might have been a streaming beta, I'm not quite sure. So I was wondering if you varied plasma beta and for the initial conditions, and even if so, how much plasma beta varied as a result of the dynamics of cosmic ray transport in your different simulations.
Yeah, that's a really great point. So the majority of the simulations were initialized with a plasma beta everywhere. And many of those simulations, like with flux freezing, the beta in the cold gas clouds will reach maybe like up to 3 or down to 3. For simulations with streaming, I also tested runs with a beta of equals 10 and 3 initially. And then those runs, the beta had a higher contribution in the cold gas cloud. And just because, kind of as an aside, so we did kind of confirm the same results that switching G found, by we repeated that kind of dependence of thermal instability on magnetic field strength.
Okay, great, thanks. And actually, I just realized that I think Frank asked a question several sessions earlier about the alpha speed in these clouds compared to the ambient medium. Do you have any idea about whether the alpha speed was larger in your clouds compared to the ambient medium, or just sort of what that structure looks like?
Yeah, so I didn't explicitly measure the alpha phase velocity, but the magnetic field in the cold gas clouds was larger than in the ambient medium. Yeah, so that's yeah, that's a great point.
Okay, thanks.
Cool. Yeah, we can do one more quick question. I see Alankar has his hand raised.
Hi, it was a really nice talk. So I saw that in one of your movies, you had this, in the strong cooling regime, you had small perturbations which was kind of growing and precipitating into the, at the bottom of the box to the stratified medium. So what's left behind kind of seems like losing this multiphase nature. So does this mean that this multiphase nature is kind of a transient in these simulations?
Yeah, that's great observation. In these simulations, yes, the multiphase medium is transient. There's no source of like any additional gas. So once the cold gas precipitates or condenses out of the medium and precipitates, the cooling time in the hot phase is so long that nothing is ever going to happen. So these simulations are set up to study kind of the growth and like the short-term saturation of the thermal instability. In a realistic system, like that, isolated patch of gas would be perturbed by like outflows or inflows, or like there would be an inflow of additional gas coming in to fuel further thermal instability.
Thanks.
Great. So that's all the questions I see. So let's thank our two speakers in this session again, and also all the speakers that we've had today.